we're going to go through this. Okay, Ikea shelf, right? These are typically designed so that they don't nail into a stud in the back. And what I mean by that is that usually in the back of the wall, they have these wood studs and they are spaced at 16 inches on center. Okay, in the corner, they wouldn't. And so when you screw these in, ideally, you'd want to hit wood behind the wall. But they don't, when you're doing something very simple like this, you're just not going to catch it. Right. And they expect you to not catch it. So just so that you have a visual of it. So let's see. Oh, okay, so this is what the construction will look like, right? So it would be like not impossible, but based on where you want your shelf, it's most likely not going to align to this. Okay. Anybody have any questions so far? I'm hoping you can see the screen, not the expectations that you spoke up earlier. Is everybody good?
Yeah, we can see it.
Okay, great. All right. So, and then we're going to make some assumptions in this example just to ease the calc and to make things a lot faster and easier and all that stuff. Okay. So, as we look at this now, we're going to first look at the mounting brackets, and then we could take a look at the analysis of the wood and all that stuff. So, so let's just say that, we have this shelf. Oops. Okay. And then what we do is we load it. So what would be a good amount of load that we can apply to this shelf? Can anybody just throw a number that you may
5
see
pounds.
possible? Huh?
$50.
50. Okay, here's the thing. If you have a little kid climbing up, chances are it might be more than 50. So let's increase it. What's a better number?
400.
Okay, fine. We're gonna do 400 and then let's see what happens. Okay. All right. Okay, so here's the thing. First, we want to analyze the wood. Now, chances are it's not real wood, but let's just think of it as wood, right? Because it's IKEA, right? So, and in real life, and from an analysis standpoint, we just kind of look at it like this, right? Is that we do this kind of simple diagram right here, and we're looking at it and we apply it. So I'm going to shortcut what the moment is, but essentially, and this is very similar to our example that we did last class. The shear diagram is going to look like this. Go right at the center, come down here, here, and then here. I don't know. What do you guys think the distance between here to here is? In the photo, 24 inches. What do you think? 2 feet? Let's go with that. So we know that this is 200 and this is 200. Okay. So first, what we're analyzing is we're now analyzing that this wood plank right here is going to be acceptable for the load that we have provided. Now, so if we do that, the question is, when we are checking the bending stress, Okay. We have a few choices, and this is where it gets confusing. Do we take the moment inertia? This face on the wood? Say it's A. This face of the wood? Oh, it didn't. I think you guys know what I mean by when I do this. I should
That one.
Okay, and then we're gonna go with football. And let me see if I could. Can I take a poll? Polls. Okay, let's see if I can do this. Okay. Great. Okay, so poll. Okay, it's been saved, but how do I? This one. Launch. Okay. So the question is, for this bending moment diagram or shear diagram, and then I'll draw the bending moment diagram really quick. Oh, shoot. This is going to be the area, so it's going to be 200 times 1, so it's going to be 200 pound-feet. Okay. So the question is, when we take the moment inertia to, because we know that stress is equal to mc over I. So the I, right? When we look at it, we have I is equal to 112 BH cubed. So the question is, when we look at this thing in 3D, is it side A, side B, or side C? Side A, side B, side C. I can't see the other screen, so if you can see that everybody has answered it or pretty close to it, let me know so I can switch back to that screen, because I want you to be able to see the A, B, and C. Oh, shoot. What the hell? I hope that didn't disconnect everything. Did that disconnect everything? You guys still see the screen?
I can still see the screen.
Okay, great. Are we close to 100%? I love the enthusiasm. It's great. It's amazing. Okay. So 75%. All right. So again, the question. Oh, we're at 80%. Let's at least hit 90%.
I don't think it showed. Well, it didn't show me like the percentage of people who like did the poll. It just showed
Oh,
me the poll.
okay. So maybe it's on my end. So you guys can see my screen now, right?
Yeah.
Okay. So we're at 88. Let's just hopefully. Oh, there we go. 94%. Last person. Oh, we got 100%. So A, B, or C. And the answer is Like, oh, it doesn't tell you if it's right or wrong, huh? Okay, so I think everybody can view it. So the correct answer, with the highest of side A being 56%, and as a class, you guys are correct at A. Okay. But remember that when we look at the beam like this, right, we always take a cut section, like you're cutting it, and you're taking that section and putting it to your face. And that face would be whether it's right here that you cut it and look at it, or right here, it's the same piece of material that's extruded, correct? Okay. And so, and I mentioned this many times, is that in other universities, there will be seniors that graduate and don't understand this concept, and they could have gotten A in strength of materials, right? And the reason for that is because the way it's being taught doesn't necessarily have the connection of everything put together, because they're like putting it by side and asking a question and not asking you to put everything together. And that's what we're trying to do in this problem here, is to kind of see it in 3D and understand and do simple analysis to solve for this problem. So if we do this, if we say that, we're just going to make numbers up, right? If we say that this right here is 1 inch, and let's just say that this depth of it is 8 inches, right? And that essentially has a surface. So if I was to draw it, it's going to look like this. One inch, 8 inch. So moment inertia is equal to 1/12. Base is going to be your 8. I to the third. So you're going to have 8/12, or you'll have 2/3 inch to the fourth. Therefore, your stress is equal to mc over I. And so your moment was 200 pound feet, 200 pound feet times 12 to get it to inches. The C is going to be half that height, right? It's going to be half that height, the C, right? So that's going to be half an inch. So that's going to be 0.5 over moment inertia that we took is 0.66 inch to the fourth. So that comes out to be, I feel good today, but I feel like I'm going to be bad tomorrow.
I got 1,818. I'm not sure if that's right.
Okay, 1818. And that's going to be in PSI. Okay. Here's the thing. Typical, like if you get like a Doug fir wood, which is something you'll get in like at Home Depot, the bending stress is roughly about 700 PSI to approximately 1100 PSI. So what does that tell us, guys?
The load is going to be too heavy.
Exactly. It's Home Depot. And then for shear stress, it's roughly around 190 PSI. It's 140 to 190, something like that. We're not doing exact numbers. We're just trying to get a point across. So if that's the case, what is our shear? Our shear is this, yes? Everybody good?
Yes.
Okay. So we know that shear stress is V Q over I T. We solve for I, right? The thickness is a width, so that's kind of given. The shear, we got it from the shear diagram. So the only thing that we need to solve for is Q, which is equal to area times Y bar, right? So if we look at the section, and we know that that's 1 inch, and then we said that that was 8 inches. we're trying to find where the maximum shear, which is at the center, right? It's right there, center. So we take the area of where we were cutting it. So the height's going to be 0.5 and the width obviously 8 inches times y bar. So y bar, check it out, is the center of that member to right here. So what is that distance?
Is it
Anybody?
1?
No, because the
Oh.
total thickness is 1, right? The total thickness is 1 inch, right?
0.25
Oh, like
inches.
that little section?
Yes,
Wouldn't it be
0.25.
0.25? Yeah.
Yes, that's correct. 0.25 inches. Therefore, a y bar is equal to 4 times 0.25, which is equal to 1 inch. Or sorry, not 1 inch, the inch to the third, right? Sorry. Right. So with that said, V was, what do we get? V was 200, right? 200. Q is equal to 1. I is equal to 0.66. T is equal to the width of that member, which is 8 inches. So what is this equal to?
37.9.
37.9 psi. So we say that if we go and buy the wood at Home Depot, it's got a capacity of 190 and your demand is 79.1. So what does that mean? Anybody? What does that mean? So to repeat the question, we calculated the demand and we explained this last class. It's like how fast you're going versus the speed limit. The question is, how fast are we going? We're going at 37.9 psi. What is the speed limit? 190 psi. So what does that tell us?
In terms of speed limit, we're under the speed limit.
Correct. So in our case, it means that the member works in shear, but it does not work in bending. So if this was to be truly loaded with that 400 pounds, it had this dimension and all that stuff, and you were to load it at the center as the way we discussed, then the conclusion is that it would be failing in bending and not in shear. Does everybody follow? I
Yes.
assume yes. Okay. Now we also talked about as a shortcut that if the member is rectangular, right? The shear stress looks like this, where it's maximum at the center, right? And if it's rectangle, we said that you could do 3/2 V over A. And let's challenge that. Okay. 1.5. B, what was V? 200. 200. And the area is 8, right? Because it's 8 times 1, so it's 8. So what does this come out to be?
37.5.
37.5 psi. And so on your FE exam, it asks you this type of question, and it's a rectangle. You know you don't have to waste time doing all this BS. You know you could shortcut it here. Okay. This is also going to most likely show up similar on a midterm or a final, right? I'm asking the students, did you pay attention in class? If you didn't, you could still get it right. But if you did, you could save some time. But understand that this works for rectangular members. Okay, so don't be like doing it to like a different shaped member, right? And then we could prove it by doing this, right? So if we were to prove it, V Q over I T. Okay. So we know that V is constant. We know that Q is equal to your area times Y bar, right? And then we know that this is equal to 112, which is 12 go here, 1, and it's going to be BD squared over 12, right? 2 cubed. And then the T is going to be a B also, right? So if we look at this, right? And I don't know how we're going to match this stuff, but if we look at this, okay, if we do just BD, that's essentially like the area. So we could just do BD squared, right? We take that out and your area goes away. Yeah, B squared D, right? If I did some algebra mistake, please correct me. I don't do as much algebra at my age. So if we do that, then we're left with 12V Y bar over BD squared, right? And if we look at Y bar is, sorry, this distance, right? That's actually D divided by 4. Does everybody agree?
Yeah.
So we could replace that with D divided by 4. And if we do that, D divided by 4, so we could say that that is equal to 3 over 1, right? We also have a V. We say that the D's cancel out. So we have B, D, V. Crap. Where's our 2? Where's our 2? Oh, sorry. That's where it is. This area, right, was this area actually, not the area of the entire thing. And so instead of B times D, when we did that, it would have been B times D over 2. And that 2 will come here. So 3 over 2 V over A. And A is the net section. It's confusing because we had really A prime versus A. And that's where so that's how we prove it. Okay? So I'm not making stuff up. Everybody good with that?
Yes.
Okay. Now, to add to that, the question could be, well, what if that 8 by 1, right? So let's say they had like 4 sheets of like wood, right, stuck together. And I'm not going to say they did this, but let's just say for fun, they put 2 nails in it. Remember that this space, again, to this question is this space right here, right? That's the face that we're looking at. And so what we're saying is that when there's layers, that means that they have layers of wood on top, and then they supposedly nailed it together. Okay, they found a really crazy nail, a really cool nail, and they did it together. So if this is a question, then it's a shear flow question, because the question is, what is the force in the nail? We'll say that this nail is spaced at 12 inches. Okay, and there's 2 of them. And we really care about the top layer being connected to everything. So if we're looking at this, we know that Q, which is shear flow, not shear stress, shear flow, is V Q over I instead, right? So the V, which is the force that we solved earlier from the strength of materials, was 200. £200. And then we got Q. Q, again, is going to be, I'm going to put A prime so that we don't get confused, Y bar. So we look at this, that's the A prime. So that, if we assume that this is 1 inch, right, it's 1/4 of an inch or 0.25. Okay. Times 8 inches, right? Because that's the width of this thing. Everybody good? And so that is equal to Q. My dumb math. I think that's what it is. Okay, so A is going to be 2, Y bar. Now check it out. We know that the center is going to be right here at 0.5. And we're looking at the center of this shaded area, which is right there, to this point right here. That's your distance Y bar. Okay. So it's going to be 0.25 plus 0.125, which is then equal to 0.375. And correct me if I'm wrong, but I think that's what it is. Right, because it's 1/4 inch right there, and then half of that, so that's 1.25. So to get that distance, 0.375, yeah, I stand by that. So if we do that, it's going to be 2 times 0.375, which is equal to 0.75. Okay. That's what it is. And we said that that's 200. We said that's 0.75. And we say that's I that we saw earlier, 0.66. So what does that come out to be?
$227.
Yeah, 227. Now, keep in mind of the units, that's pounds per inch. Got it. So now if we have 2 nails, right? If it's got 2 nails, I'm just going to Q prime per nail. Then it's going to be half of that, which is equal to 113 pound per inch. A nail, right? You see that nail? So that single nail is taking 113 pounds per inch. And what is the spacing? Remember, what it means in this diagram right here is that that nail is down here, down here. You're going to put another one here, 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 here. Right? And so the spacing of these nails are 12 inches. That's what it's saying. And people get confused because they're like, it's talking about different planes. And that's why this question is like so confusing at times. Right? So you put another one here and for here. That's what it's saying. And within that, you have 2, right? So that's why when we're talking about single nail, where Q nail is that, and then what's the force of the nail? Well, it's simple. Well, we have a single one of the per nail, right? Divided by inch, just multiply by 12 inches. Well, guess what? The unit cancellation gives you a force, hence F. So we take that times that, we get 1,363 pounds of force, and that's in shear. So what that means is that when you have the nail in there, the shear force on that nail because of the load is 1,363 pounds. Any questions so far? So what we've gone over so far, statics, strength of materials, and topics that we covered. Well, under statics, we did shear and moment diagram. Then we took it to bending moment. We talked about moment inertia, we talked about shear stress, then we talked about shear flow, right? And all by this, right? Super simple, something that you just get from Ikea, right? Really cool looking shelf, and you can analyze it. Any questions so far? Anybody need some kind of clarity, or we're good? Or
Will these problems always consider the top layer only?
say it again.
Or will these type of problems consider the
Yeah,
top
okay.
layer?
Correct. So the question that's coming up is right. Is the question always going to be considering this top layer? Okay. Um, okay, I would say that within the like the midterm, it would be always the top layer. I mean, it could equally be the bottom layer, right? Another question could have been, well, what if you already have these two members that are glued together, and then you're just nailing the two together, right? But for the simplicity of these type of questions, it's going to be most likely like the top layer or something like that. So not a guarantee, but okay. Any other question as we look at this beautiful bookshelf? And you could obviously, at the beginning when somebody said 50 pounds, maybe that was a logical, correct answer, right? That it's really not intended to be taking more than 50 pounds. And chances are this is not solid wood a lot of times. What they do is they actually have like this nice kind of laminate piece on top and bottom, and inside, like I kid you not, sometimes it's like cardboard, like but really good, like honeycomb type cardboard, right? And I mean, people say IKEA is cheap, but you gotta understand, like it's like affordable to begin with, right? So you can't say that it's expensive. I mean, IKEA is not going to strive on being like expensive price wise and cheap material wise. To me, I think it's like engineering genius in a sense that what they're doing is they're really pushing a lot of their products to close to like the max stress load that they wanted to design to, right? And they pull back and say, well, how do we approach this without wasting money on taking a solid wood? Well, and they come up with all these ideas and they test it along with calculations, and then they come up with these products. That's why they a lot of times feel lighter than other products, comparable products, because they're trying to engineer it to the load that you're applying it to. If you take those old school furniture, man, sometimes you could take like 1,000 pounds and it won't break. But the question is, are you really going to put 1,000 pounds on like a shelf, right? Are you really going to put 1,000? And the answer is no, right? And for 98% or 99% of people here, this is what they're going to do. They're not going to load it at 400, 800,000 pounds. They know that this is the intended design mode. Now, here's the thing. If, for example, you do exceed the load, right? And you pay $20 for this. I don't know how much it was. Shoot, $38, sorry, plus the hardware. My point is a commercial company that's going to use it for heavy loading to put 1,000 pound, and if it breaks at $38, they're not gonna be like, oh, I hate IKEA. They know that they bought something that's not designed for that type of look. All right. Any other questions before we proceed to the next topic? We good? Okay. So the next thing that we're going to be looking at is we're going to look at this stuff. Okay. Now, here's the thing. We were saying that it's 200 pounds, right? Was the reaction, right? So that 200 pounds so we're done analyzing the wood. That force comes over here and puts a point there. Now, if we say that it was like equally loaded or equally distributed, that 200 pounds goes in the center of that member right here. And essentially what you have from a free body diagram is that you have a cantilever member, right, that has a point load, right? Now, you could conservatively say, hey, you know what, sometimes, I might put that 800 pounds or 400 pounds at the tip of it. Then that actually moves to right here. Is everybody kind of seeing that? As I move it from like we're originally centered here to there, that reaction comes over here and it's going to do it this way. So what that means, right, is this. from a statics. And this distance. Right, super confusing. You know, they say height, depth, all that stuff. All they're trying to say is that from here to there, 11 3/4. Like, seriously, let's just do 12 inches. Just keep it simple, right? So we know that this distance right here is a 12 inches. Okay. So the question is, well, how do we analyze it, right? So what I've done is that I've taken a three-dimensional problem and looked at it from piece by piece. That makes a two-dimensional analysis that we traditionally do in the classic school case, right? And then taking that and put it to another two-dimensional question. Now, the question is that, well, could we have solved it three-dimensionally? And I would say, yeah, we could have done some matrix and all that stuff and do something pretty wild. But we got to be realistic here. Like, if we do that, then you would probably screw up somewhere in your math. That's what matrices does for you. And right here, when we simplified it, even when we simplified, it was pretty math intensive. You know, maybe it wasn't. But the point is that we took something that was complicated and simplified it to 2D. We analyzed it, and everything we've done is, for the most part, legitimate. Like, all our calcs, everything, you know, assuming that you guys gave me the correct answer, the calculation when we put the numbers together is all right, then everything what we did is legitimate and it's proper. And, you know, from a plan check standpoint, if you're submitting these calcs, assuming we clean it up a little more, it's totally viable, right? Everything works, right? Well, I mean, it didn't work, but their approach is correct. Okay, so going back to this problem, what I've done is I then taken that three-dimensional stuff, showed it to the bracket, and we're analyzing the bracket right now. And we could have done the same thing, even though we're not going to spend the time to redo and change things, but we're going to be talking about that. You know, we could have drawn, you know, what we could have done is drawn the moment diagram like that. We could have drawn the shear diagram like that, right? And the shear diagram would have been like 200 here, right? And then 200 times the 12 would have been 24 2,400 pound inches, right? Would be the max moment right at that point. And then we could have just applied what we learned, right? Is stress is equal to MC over I, right? Shear is equal to VQ over IT. Now, let's try to change it up just a little, right? Not necessarily solve it, but we assumed, okay, I know that this is showing that it's like open, right? And again, like I said, like least amount of material as possible. That's the IKEA way. But that's too hard for our class. Not that it's too hard, but it takes too much time. We're going to assume that that's solid, right? If we assume that that's solid, the original assumption is that we said that it was centered right at the member, right? But what if that was coming out to a little offset from here? And let's just say that that is 1 inch. Essentially, what you have, in addition to your shear diagram, your moment diagram, you actually have a torsion diagram. And that torsion is going to be constant. And it's going to be your force or torque is equal to, you know, force times your radius. In this case, we're saying it's a block, even though I should have said it was circle for simplicity. And we're saying that this whole block is 2 inches, right? And half is wedge. So what we're saying is that the force is 200 times the R, which is 1 inch. So we can also say that torque is that. If we do that, then we have that famous equation of Target, right? Target, that torsional stress due to torsion, right? Not due to shear, but due to torsion is equal to Target. Torque applied, radius, um, polar moment of inertia, right? And then from there, we could have got in and then the angle of twist. And remember, if we don't remember what the formula for angle of twist is, what we could have done is say that we said, remember, don't hit the player, PLREA, don't hit the player, hit the game. And we would say that the angle of twist is equal to TL, right? Because it's the similar, like transform, like Stranger Thing type stuff, right? What is it in the other world? So this is the same. E, right, would be G, right? And A in the case of this would be J, right? Because this is geometry. And so we could, if you remember, don't hit the play, hit the game formula, you could kind of derive the angle of twist, right? And we could have solved it that way. So what we've done so far is we've actually taken a lot of stuff from what we learned in midterm 1, some of it a little past that, to kind of put it all to one thing. Now here's a final note. If we look at this bracket right here, and we determine that it's saying that it's like right around 5 inches, let's just say that it comes in, and let's just say that this, for fun, for 4 inches, and you apply a moment here. Later in your other classes, what you'll find out is that there's something, and actually you learned this in statics, so I'm just going to reiterate it. It's one of those things that you were taught, you probably didn't pay attention, but we learned that there's something called a force couple, right? That essentially is equal to a moment, right? So when you're applying this load, that creates this moment, and in this case, we said that it was 2,400 pound inches, 2,400 pound inches. Now that, and then we also have a shear. This screw, nail, whatever you call it, is seeing two things. One, it's seeing a force couple due to a moment. And so what it's seeing is that when you apply this load, this is going to pull on that nail, and that's going to be pushing on the nail. In other words, you can't really push a nail because this bracket's going to push into it. So this tension force, remember that a moment is equal and opposite with a set distance, right? So if we know that the moment is equal to force times distance, and that's your force couple, then, and we know that our moment is 2,400, and we know that our D is 4 inches, as noted right there, right? Then the force applied is what we solve for. So then force is equal to 2,400 divided by 4, which is equal to 600. Yes, 600 pounds. Right. So what that means is that that screw that's connected in there is going to feel a tension force of 600 pounds. Okay, which is a lot for a drywall screw, because usually they're only take like 40 pounds or some stuff like that. Okay, so in other words, if you're low with that 400 pounds, the wood wouldn't break. Okay, this I know that we looked at it with the wood. We say that the moment of this would not take it for the 400. What actually would happen as a failure mode, now that we analyze this, is that this is going to come out because this bracket's going to fail, and the load that's being applied is 600 pounds. So if you're really going to design it for that, you actually have to put it aligning with the wood stud behind. Okay. Does anybody have any questions? I hope this was like an alternate approach of really summarizing a lot of things that we looked at into one kind of class that summarized a lot of things that we've learned about strength of materials up to this date. So